As you can see, time is 2 minutes to 9. I'm just about to present a lesson, and I understand important officials from my employer will be in this particular lesson. So I'm very excited. I'm checking everything. I've already logged into the classroom, and I've checking that everything is all right, starting from my lesson plan, which is already there. Of course, I've muted the microphone just in case somebody comes in and finds me in the class and talking to myself and wondering what is happening there. So the first thing is the lesson plan. I've got the reference materials, which is from our KLB textbook. That's where I will refer my students to. I've got my favorite class presenter 3, and it's a very good software. It allows me to ink the blackboard or the whiteboard in real time, and that one is good. Let me check whether anybody has joined me in the classroom, waiting for others to join. So it appears as if I was very early. Students may not be there actually, I don't know, but they were there yesterday, so I expect them to be there today. Let me see what else. I've got my PowerPoint presentations ready over here. What I'm really going to talk about, starting from the first slide there. So I'm ready for that. Let me check what else is there. What else is there? This one, I don't need it. This is just something I downloaded from the internet. And then I've got the various tabs. They're already opened for me to be able to use. So maybe I can close the ones which I feel that I do not need right now. And I can see somebody has already joined in.
Naona tuko wawili tu.
Tuko wawili. Tuko wawili.
Ngoje wanafunzi wakuje.
Wacha ningoje. Yeah. All right. I can see there are a number of students who have come. Good morning, class. I need somebody to speak to me to tell me whether you can be able to hear me.
You can hear you, sir.
Okay, thank you very much. I think I can go right ahead with my lesson. So, first of all, I want to start by apologizing for yesterday's lesson, where it was terminated somewhere in the middle. It was due to a sudden blackout from my end as I was looking for something, and then that blackout persisted for a very long time. So these are some of the challenges which we are encountering. So sorry for that. Otherwise, whatever I intended to teach yesterday is what I would like to go straight to. And let me just go to sharing of my screen. With you, so that we can be able to see what I have prepared for you today. Okay, let's go through the lessons for today. We will be studying the topic waves 2, and the subtopic we are going to look at is reflection of waves. And the objectives are as follows. By the end of this lesson, I'll expect you to draw or to complete a figure to show how plane waves are reflected by plane and curved boundaries. I will spend some time on how plane waves are reflected on by straight barriers, because the same concepts will be used for curved boundaries. Now, I expect that you have learned about reflection of light at plane surfaces. That is a topic in Form 1. And of course, the third topic in Form 3, which is refraction, I expect that you have gone through those. But for today's lesson, I just need you to have studied reflection of light at plane surfaces, especially the laws of reflection. So let me go straight to the introduction bit of it. Over here, we are dealing with waves. Allow me to do something here so that I can bring in a few things that are going to remind us about waves. When we are talking about waves 2, it is expected that we have studied waves 1, where we defined concepts or physical quantities such as amplitude, frequency, periodic time, and the speed of a wave. We also studied situations whereby we are able to generate waves. For example, this one is a rope. When one end of a rope is moved up and down, we generate some kind of a wave. So when the idea of a wave is mentioned, what comes into mind is something which looks like that. At our home front, we might be able to see something which looks like this. On this, on my camera here, I have this cardboard. This is part of a cardboard that I've been able to remove the center part of each of it, which is corrugated, and you can see the way it looks like is exactly the way the waves that we have just seen look like. Let me do something here so that it doesn't hunt a lot when it is focusing. Yeah, there. So those are the kind of waves that we are going to generate. It's more like what now you can see here. So on the home front, if you'd like to understand much more about waves, just get a piece of cardboard, remove that center corrugation, and this is the way it looks like. Another example that you might want to use is when you look outside, you'll be able to see the iron sheets. The iron sheets have got these particular shapes. That is exactly how waves look like, especially those which can be seen with our naked eyes. They look like that. If you go to the swimming pool, for example, and you look at the side of the swimming pool, you'll be able to see what I've just shown you using this. So I'll come back to this camera where we are going to do a bit of drawing. For now, I want to go here so that we can investigate a little bit more about that. For example, when we talk about water waves, here I've got a repo tank. It's just a simulation that will help us to understand what is happening here. And when we allow drops to fall on the water, I'm going to allow the first drop to drop, and continuously like that, you can see that now we are going to generate circular waves. How does this happen? What are these bright rings and dark rings? So I want to explain those one briefly, how they come about. And maybe I'd better have the same simulation playing. Let me just put it at the side here as I show you how that one comes about, because it is important for us to be able to understand that. So on the right hand side, I've got this blackboard over here. So I'm going to try and draw the kind of wave that we have seen. If this is the surface of the water in a swimming pool, and let's assume Actually, let me just talk about the ripple tank, because the ripple tank has got a piece of glass at the bottom. It is transparent. There is usually a bulb here at the top, a bright bulb that illuminates the surface of the water. This is the depth, and this is the flow. Now on the floor, we can put a white manila paper, and then we will stand at the side here and look at the flow. Look at the flow. We can also use something else we refer to as a stroboscope to try and freeze the waves. But for now, I want to show you how these bright and dark spots are formed. So when the surface of the water is disturbed, some of it will move up, some of it will move down. So what I'm drawing here is what you would see at the side of a swimming pool, for example. All this is water. Below here, it's water. A chunk of water has moved up, an equal chunk has moved down, and it generates a wave. Now, this section here behaves like the curved surface of a lens. Let me just briefly talk about lenses. This one is a lens. When parallel rays of light, sorry for that, this one is too dark. When rays of light fall on a convex lens, they get converged at a point, which we call the focal point. So if this is light, over here we are going to see a very bright spot. Very bright spot. Now, this one is a convex lens. For a concave lens, which looks like this, the concave lens diverges rays of light, so they don't converge. It diverges the rays of light like that. So this space, this particular spot here will appear to be less bright or dark, while this one will be bright, and this is dark. That is how these dark and bright spaces are formed. Let me just freeze it. This bright space will represent a wave front, and it is part of a wave we call a crest. A crest looks like that. Sorry, a crest looks like that. This dark spot here is a trough. A trough looks like that, and then followed by another crest. So definitely where there are crests, it behaves like this type of lens, where the rays are going to get converged, and it produces a bright spot for this lens here. And where we've got a trough, it produces a dark spot. So we are going to have bright, dark, bright, dark, bright, dark, because we are looking at it from above. How about if we look at it from the side? You can see this is exactly what I've been able to draw. Apparently my wave, the amplitude of the wave does not reduce, because I'm assuming it doesn't lose any energy. But this simulation here shows us that wave, because it loses energy as it goes from the source, the amplitude, which represents how much energy a wave has, reduces as time goes by. I want you to ignore that and concentrate on the fact that we've got crests. You can see this where my cursor is, a crest moving like that. We've got a trough moving like that. And that is what we were able to see, the crests moving. Again, look at my cursor over there, like that. Now, why is this crest like that? Why is it so long, while for mine here, it is just a single spot? You see, it was just a single spot. But this one appears to be elongated like that. It's because if I come here, this is a two-dimensional impression of a wave. If I want it to be three-dimension, let me just try and draw something. I'm going to draw something that I've just shown you using the cardboard or using the iron sheets. And the moment I drop that, I've got my cardboard. There it is. Now you can see it is three-dimensional. Three-dimensional shapes usually have got some length, they've got some height, and they've got some thickness. And that is what we saw on my piece of cardboard. Over here, you see, that's what we saw. My piece of cardboard is three-dimensional. I drew that, and then I was able to also show you how these ones come about. Again, let's put it away because I'm just using that piece of cardboard so that when we draw waves like this, then you won't have a problem when we say, see these straight lines that I've drawn here? These ones? Of course, this part of the wave is referred to as a crest. This is the next crest. This is the next crest. The distance between any two adjacent crests, this distance here, is referred to as the wavelength, and it is represented by that funny Greek symbol. We have talked about that one before. Again, this one is another wavelength. I'm sorry if my diagram is too small because I know some of you are using mobile phones. Should have drawn a much bigger diagram, but I think that one is going to help us all the same. Let me see whether I can do something here. Oh, that one is something that's going to help you now to be able to understand what is happening. So these lines that we have here are the ones that now I'm going to draw in the next diagram, and I'm going to say as these waves travel, this one is a crest. It's made up of so many crests, so many crests. I'm looking at my cardboard from above. I want you to be able to understand that. The next crest is here. The next crest is here. The next crest is somewhere there. You know, so many of them. And in between any two adjacent crests, there is a trough. Don't forget that. Crest, crest. In between, there is a trough. Over there. Okay. Now, this wave is traveling to the right. Or there's something else. The waves that I've just shown you on the simulation were circular. They were circular, but now I'm drawing straight waves. How is this possible? This is possible because instead of this drop here, we can have a straight piece of wood which we are going to take all the way up to the almost touching the surface of the water, and then we use a motor to make that piece of wood to vibrate. In that case, that piece of wood will be something like this. And since it is in contact with the surface of the water, and there is a motor here which is vibrating, this piece of wood is going to vibrate and it's going to generate straight waves. These are what we call plane or straight waves. That is the wavelength. This is another wavelength. So just in case somebody gives you a question and asks you to identify the wavelength, get your ruler, measure that distance, and you're good to go. So I wanted to explain those things first before I go to the various properties of waves that we are meant to study. Now, in this topic, waves 2, let me just go into slideshow. That one is much better. In waves 2, basically we are going to look at 4 properties of waves: reflection, refraction, diffraction, and interference. We have done a reflection of light somewhere in Form 1 when we did rectilinear propagation of light. So that one is an area that I'd like you to go and review. We've done a refraction in Form 3. I think it is the third topic. Now we will study, we will start from reflection, go to refraction, diffraction, and then interference. Now, this is a possible question that you can get in the exam. I want you to look at this question, then we look at the solution, and then we go back and see what is it that we ought to have learned in order to be able to answer this question. The figure shows straight water waves incident on a straight barrier. This orange boundary here is the barrier. And now we know how these waves have been generated. We have got no problem with that. We are asked to complete the diagram to show how the reflected waves look like. So you will have to draw. And that is why I'm using the second camera, so that you won't say, okay, the teacher is using computer to draw, that's why the diagrams look so neat. I will show you using the second camera how I also draw. And I know since you're at home and you've got a pen and paper, I'd like you to identify those skills that I'm using in order to be able to do this. And we are expected to draw at least 4 reflected wave fronts. This is a wave front. That straight line that joins points on a wave which are at the same distance from the source. That straight line is referred to as a wave front. This point here where my cursor is a point from the source. Maybe the source is here, that distance. Another point which is exactly at the same distance from there is this one here, or this, or this, or this. Now, if we join all those points which are at the same distance from the source with a straight line, it makes a wave front. Better still, these are crests, like we saw on that carbon, on the iron sheet or on the carton. Right. Now, this is how the answer will look like that, for 3 marks. Now, very many students usually don't know how this diagram comes about. And when you draw, many of us do not draw it correctly. So in this lesson, you will be able to draw it correctly, to draw exactly that diagram exactly. So, this is the simulation that shows how those waves are reflected. The waves which are in black are the incident waves. They come, they hit the boundary, and then they are reflected like that. How do I get to draw this kind of diagram? So let's head over to my, let me just end that so that I can go back to my camera over here, because this is where now I'm going to do some drawing. So arm yourself with your pencil, plain piece of paper, and then we do some drawing. Okay, before we do that, I'd like to review. There's something that I had drawn over here. Okay, fine. How does it look like? It is on the other side. I had drawn something on this paper here showing, yes, that is it. Now the letters are the right way up. There we have it. Now, this is a mirror. This is something which we have done in Form 1. There's a mirror. This is the incident ray. And this is the reflected ray. This is the point, if you can remember very well, is the point of incidence. And at the point of incidence, we draw a line which we call a normal. A normal is a line drawn at the point of incidence such that it makes 90 degrees. This angle here is 90 degrees. That's why it's called normal. Normal means perpendicular. Perpendicular means 90 degrees. The angle between the mirror surface and the normal is 90 degrees. So the normal is usually drawn at the point of incidence. Why point of incidence? It is the point where the incoming ray, which is the incident ray, strikes the mirror. There. And then after that, it's going to be reflected. Now, how do I ensure this? I ensure this by making sure that the angle of incidence, which is the angle between the incident ray and the normal, is equal to the angle of reflection, which is the angle between the reflected ray and the normal. And be very careful. Sometimes you can be given this angle, and when students are asked to identify the incident ray, they quote this angle. No, remember the definition. The definition is the angle between the incident ray and the normal is the angle we refer to as the angle of incidence. And the first law of reflection tells us that the angle of incidence is equal to the angle of reflection. So far, so good. I now want to go into the question which we have just seen. And in order to do that, I require a bit of space. So what I'm going to do, I'm going to raise my camera a bit. So it's going to get disturbed, to disturb us a little bit, but just be patient. I've raised my camera to some good height so that I can have some good drawing. And because I want you to see everything clearly, let me try to focus. And there, you've got a sharp point which is well focused. So let me remove that. And now I want to do some drawing. What do I need? At home, you have your ruler. You have your ruler. For me, I've got this ruler that we use in technical drawing. And the first thing I want to draw is the barrier. Here I have the barrier. I want it to be as thick as possible so that for those who are using devices with the small screens, like mobile phones, it's going to be big enough. And then the question was such that there was some wavefronts. I'm going to use the size of that ruler to make sure that the wavefronts are equally spaced out. In other words, the wavelength is the same. Something like that. And let me draw another one here. No problem. Something like that. Now, this was the question. There is a barrier. There is the incident waves. And now I'm required to draw the reflected waves. How do I go about that? This is what you do. You measure or find the center of one of these lines. Approximately, I can say it's somewhere around here. Okay? And then, using your protractor, draw a line which is going to make 90 degrees with it. You see where I've put my ruler there? Let me use a transparent one. Oh, not completely transparent, but it's much better. There. You try and draw a line. That line should make 90 degrees with this other line. And it's drawn at the center. What am I drawing? I'm drawing the incident ray. So what we did in Form 1 is we avoided the wavefronts and just drew the incident ray. The point where the incident ray strikes the mirror or our barrier, what do we draw? I know you have said we draw the normal. I don't want to disturb you because I know you're very busy drawing what I'm doing here. The normal is a line which makes 90 degrees with the boundary. Okay, before you can be able to approximate your measurements the way I'm doing here, you can see that mine are just approximations, but they look as if it is 90 degrees exactly. This comes with the practice. So for you, I expect you to use a protractor to ensure that that is 90 degrees. You know, don't draw a line which looks like that. I've seen students drawing something like that, and then they tell me this is 90 degrees, but even from the eye level, you can be able to see it's not 90 degrees. So use a protractor to start with. So point of incidence, we draw the normal. We measure the angle of incidence. Again, I repeat, the angle of incidence is the angle between the normal and the incident ray. And then we are going to draw a line which makes the same angle with this one. The same angle. If this is 30 degrees, we draw another 30 degrees here. Okay? Once we identify that point, we draw the reflected ray. See? We draw the reflected ray. And now we are almost getting all our marks. All our marks. Then, in order now to draw the reflected wave fronts, they must be perpendicular. Okay, first of all, there is something else that is very important. I'm going to use my pen, hoping that it's going to be as faint as possible. Do you see the edges of these lines? I draw a line and I extrapolate it until it touches my boundary. I come to this other one here. I draw another one until it touches the boundary. But remember, they are very faint lines that you can be able to erase. So you use a pencil. Once you identify this point and this point, you are almost there. You'll come here, put your ruler in such a way it is parallel. This face is parallel, and then just slide that ruler like that, such that the other line that you want to draw like that is very faint, is going to be parallel to this one. And you repeat that with this other point. Slide your ruler like that until you can be able to draw something like that. Let me shift this one a little bit so that you can be able to see that part which can't be seen. Having some difficulty with this, but not to worry, everything will just be fine because I had fixed it onto my whiteboard. Okay, there. Let me just slide it a little bit because I want you to be able to see everything properly. There. And we are now set to continue. Okay. Sorry for any kind of mess, but I know we are okay. Now, these are the guidelines. This is the first guideline, second guideline. And then the lines which I want to draw must make 90 degrees with the reflected ray. Remember, this is the reflected ray. So I'm going to start from here, and I can position my ruler in such a way that I can even start from the middle here, or from that point, because I want to draw my first line. And you can be able to see that the line that I'm just about to draw, this one, makes 90 degrees with this line and also with this other line. Just watch that. See that line that I've drawn? Makes 90 degrees with this. And then, remember, I used my ruler to identify the amount of wavelength, because this is the wavelength. That is the wavelength. So I'm going to use the same ruler and draw the next one. There. These are now the reflected waves. The next one here. Neither too big nor too small. I use the boundary lines to guide me on what to draw. And then I proceed. Next one there. They said draw at least 3 wavefronts. I've drawn 4. I've drawn the 5th one. And there we have it. I can just continue and continue and continue. This angle here, okay. In the video, it appears, yes, it appears right, because on my screen, I can be able to see exactly what I'm showing you here. On the real paper, it appears 90 degrees. On the screen, look at it. It also appears 90 degrees. Something to be careful about here, I've already talked about that, is this wavelength here. Because in reflection, the quantities, nothing happens to the speed. The speed remains the same. Because the speed of a wave is determined by the medium through which the wave is passing through. This is air. This is air. This is air. The incident wave was in the air. The reflected is in the air. So nothing happens to the speed. The frequency, nothing happens to it because the frequency is just determined by the source. The source. In this case, the vibration of the motor. Because the speed of the motor was the same, then the frequency of these waves is going to be the same throughout. And nothing happens to the wavelength. All these factors remain the same. You see, this is what the examiner will be checking for. They will check, have you tried to draw some kind of wave over here? Let me just pretend to be an examiner. Okay, has the student shown any kind of incident wave over there? Yes. Has the student drawn some kind of normal here? Tried to approximate this to be equal to this again? Yes. Has the student drawn this? Has the student now drawn lines which are perpendicular to this other one? Yes. And of course, neatness. My marks are 1, 2, 3, 4, 5. I had given you 3 marks probably for they will combine some of the marks, maybe this one and this one and this one, to be just be 1 mark. Once we check for 90 degrees here, we don't have to ascertain it here. But the mistakes I've seen students make is this. When they draw this, they just draw lines which are like this. They don't care whether the wavelength is the same. They don't care whether the wave front is perpendicular to the reflected wave. They don't care about that. And that appears to be the major problem with this kind of work. So that is what I wanted to illustrate on my whiteboard, and I hope you are getting the point. When we go to my answer, because this is what we said. We said the answer looks like that. Let me see. That was a simulation. In the short notes that I'll be giving you in our Google Classroom, they will have some of the images that I have in this simulation, and so don't worry. The points to take care of are these. Draw the incident and the reflected rays. I've shown you how you do that. This is the incident ray, this is the reflected ray. Identify I and R. I is here. Let me just, I don't have to struggle so much because I've got some kind of pen here. Yes, can you hear me?
Yes, I had some problems in hearing what you're saying.
Yes.
Could you go back to where you were drawing there?
Or where I was drawing? Oh, this is I, sorry, this is I, this is R. Okay, no problem. Let me go back to that one. I put this one away. Discard, no, just discard that, and let me then go back to my drawing. Okay, here we are. What was the question?
Yes, now in the part of now drawing the, after I have drawn the reflected ray.
Yes.
Now, when you're drawing, could you repeat the part how you draw the wavefronts?
Oh, the wavefronts. Okay, now I've got your question. You are at the point where you have already drawn this. Now you're wondering, how do you draw these ones? What are the rules? Okay, rule number 1 was These blue lines that I had drawn here, they are guides. I must make sure that I also draw that in pencil, which I can easily rub, okay, in order to identify this point where my finger is. I also draw this other one here, such that they are touching the wavefronts of the incident wave. This line here, I also identify this other point here. If I do that, I draw another line, this line here, which is parallel to my reflected ray. I draw it like that. And from this the same point, I draw a line parallel to the reflected ray, like that. That one guides me as to how far my wave front will go. It can't go beyond, and it can't be too short. It will just reach there. But remember, these are just like construction lines that we do in technical drawing. Construction lines. They help us to identify before you can get the actual drawing. They help to guide us. Next, now you want to know how I draw the red lines. At least you know the boundaries. The next thing is these red lines, you could draw them starting anywhere. Here, you can start from here, you can start from anywhere, but I would recommend you start when the wave has made one complete wavelength. That's why I used this ruler, because this ruler has got the same wavelength there. I come and align it such that it touches that point, and then I draw this one here. It starts from there. When it comes like this, it stops here, because this line, it can't, this is another medium altogether. Maybe this one is glass, you know, something like that. The next one starts from here and ends here. Then I put my ruler again. Starts from here, ends here. Remember, I'm using the width of my ruler to stand for the wavelength. Right. You are now wondering, as I draw them, what must I keep in mind? This is it. You must keep in mind the line which you want to draw must be making 90 degrees with this reflected ray. So I draw the first one like that, but I had in mind it must make 90 degrees. I did not just come and draw any line like that or draw any line like that. No, I did not do that. That would be wrong. I had to make sure, okay, fine, I want to draw it at this point, but it must make 90 degrees with this line. So I have to position my ruler very well. So when you are at home and you're trying to practice on these, use your protractor. Put your protractor here in order to ensure that that one is 90 degrees. My protractor is a little bit far away from my table, otherwise I would have shown you how that one is done. So make sure that the lines you draw make 90 degrees, with this reflected ray. And then after that, you will get your rubber. Rub all this. You'll get a very neat drawing. Very neat drawing. So I hope I've answered your question. That one helps you a bit. Okay, now if we go back to our textbook over here, because this is what you see in our textbook. Let me just reduce a bit of that space so that majority of it can be seen. I talked about refraction, and you can see refraction is one of the topics that you have already done before you do waves 2. When you go to Form 1, there is this topic number 8, rectilinear propagation of light. I'd like you to review those points because those points are the ones which I'm using. The angle of incidence is equal to the angle of reflection. I'm just scrolling through the various pages so that I can be able to show you that. You see this? This is where we studied the laws of reflection, and you've been able to see that even in the diagrams I'm drawing with the wavefront, I'm making sure the angle of incidence, this much, and the angle of reflection, they are equal, although I just estimated. So some reviewing for you to do is you'll go to chapter number 8, of course, in your notes. If you don't have notes, you'll communicate with me in the Google Classroom. I see how I can give you some short notes on the same, but short notes usually will help you if you have attempted to read in details the content. So go to the textbook, read that, and then my short notes are going to assist you. The next one is a refraction. Probably today we won't look at a refraction because I have to bear in mind the time that I have, because I had set this for 1 hour and I can see I've got about 10 minutes, so we can't go into refraction. But I'd like you to read, because those are the concepts which are required for you to be able to understand waves 2. Now in waves 2, your school may have a ripple tank. It may not have a ripple tank. If it doesn't, you have seen a swimming pool. This swimming pool has got a transparent bottom here, and this is where we put a piece of paper, and then we've got a stroboscope, and then we are looking at the waves. The stroboscope tries to freeze the waves. I'm sure in a movie you may have seen a car moving to the right, but the tires appear to be either rotating in the anti-clockwise direction or freezing. Okay, that concept is the one which is used in the hand stroboscope to try and freeze the waves. The motor I was talking about is this one. The piece of wood I was talking about is this one. And of course we've got these rubber bands or strings. And of course the lamp to cast an image of this crest onto the floor. There are a lot of materials to read about. I explained how the bright and the dark regions are formed. We have just seen in our simulation how circular waves are formed. You just need to get a dipper, and it's going to disturb the water at that particular point to produce circular waves. And what I've mainly dealt with today is this one here, how you get to draw this kind of diagram. Yeah, so I'd like you to make use of your textbook, read on those, so that in our next lecture you'll be able to understand some of the things you're going to see in my simulation over here. So before I went to answering your question, I was here where I was trying to explain the most important things here. Draw the incident and the reflected rays, that and that, and now you know how to do it. Center of this line, draw a line perpendicular to it, draw it all the way to the barrier, call that point the point of incidence, draw a line which makes 90 degrees with the mirror at the point of incidence and call it the normal, measure the angle of incidence, measure an equal angle on the opposite side and call it the angle of reflection, and you make sure that they are the same because you're using the first law of reflection. The angle of incidence equals to the angle of reflection. Then observe the following points. First of all, I've already talked about perpendicular. I cannot overemphasize that point. It is so important, so important. Even if your teacher does not draw it correctly, now I expect you to draw it correctly. And of course, bear in mind, in a reflection, there is no change in wavelength, no change in speed, no change in frequency. And we know exactly why that happens. The frequency is that of the source, so it does not matter the medium through which the wave will travel, the frequency remains the same. The speed remains the same because the medium has not changed. The medium through which a wave travels is what affects the speed of the waves. The wavelength, of course, now depends on these two. A change in any one of them leads to a change in wavelength, and we are going to see this in refraction. Because in refraction we are going to have waves moving from one medium into another one. And of course I've already explained this. The wavefronts are perpendicular to the rays. Now there is this one. This one is a very simple one in the sense that the black waves now are moving towards the barrier here, and over here the angle of incidence will be 0. Many times when I ask students, what is the angle of incidence here? They always say it is 90 degrees. And then after some deep thought, Some of them just come to their senses and they realize it is 0. Notice that the incident ray is along the normal. So that's why the angle of incidence is 0. So the black waves get reflected right back. You can see the orange waves are being sent right back. So I've made this simulation such that it repeats itself over and over again. And that gives us a clear cut point on what is happening. The next one is a reflection by a curved barrier. And because we've got about 6 minutes, I'll just show you how it takes place, and then you will go and design or draw using the same skills of reflection, how the reflected waves look like. The black waves are the incident, the reflected are the orange ones, and you can see they appear to converge. To converge is to come together as they travel. They come together as they travel. They appear to converge at some point here. At some point here. So, how do we get this kind of wave? How do we get them to behave like that? Perhaps if I go back over here. Now, this is what happens. You see this wavefront here. The first part of this wavefront to strike the barrier is this one. And I'm just saying, let me do some writing over there. You see, I can call this point A, point B, and point C. So the first part of the wave to strike the barrier is A. So while B is still on its way to the barrier, or some point here is still on its way to the barrier. So this point here, X, which is still on its way to the barrier, the moment it gets to the barrier, the reflected part of A, which we can call A dash, is here, while X has just reached the barrier. Then, when this other point just reaches the barrier, or maybe when C, see, this wave now will be here. It is still on its way towards the barrier, so C will be here. So when C reaches the barrier somewhere around here, yes, somewhere around there, or let's say somewhere around here, B will be here. This one will be B dash. It will have been reflected. And A dash will be here. So this wavefront, it's not the whole of it which strikes the barrier at the same time. It is just a part of it. So that part that strikes the barrier is the first one to be reflected, although its other part is still on its way towards to the barrier. Yeah, like for example here, it's just A dash X that has been reflected. X, B, and C are still on their way to the barrier. I hope you can see this small dot that I'm using over here just to illustrate that particular point. So the point I'm making here is A and A, B, C do not strike the barrier at the same time. Let's go to the curved, because I want to give you some guidance so that when you will be giving me the answer. So if you call this part A, B, C, which parts of this wavefront are the first ones to strike the barrier? Using that, I expect you to be able to come up with the shapes of the reflected waves. And if you're using a computer, I want to challenge you a little bit more. You're a student, fine. You may be a computer student or not. Go to PowerPoint, try to make something that moves like the one that I've made here, and it is also moving. Spend a little bit more time with that content in order to fix it in your mind. Don't just look at it and then you leave it at that. No. Go and do something with it, including the piece of cardboard which I had recommended. In fact, let me just keep that because I might need you to see it later on. Including that cardboard. You see that cardboard that we were using there? This is the way the waves are. You see, if I look at them from the side, that's the way they are. So the distance from one crest to the next is what I have here. Of course, this one is so big, you know, and these waves are moving like this. How do they turn now to be like this? I've already explained, but you can design something which is 3-dimensional. And maybe at that point, I would like to bring our lesson to a close. Unless anyone has a question, because our time is up. It's already 10 o'clock and I want you to be ready for the next lesson. Any question? No question. I'll be able to see you next lesson. Bye-bye.
Bye.